All right, everyone. How are you guys doing? Yeah. Me too. Can I ask you guys to stop talking, please? So today we're going to continue on with Chapter 3. So in Chapter 3, our main focus has been techniques that we can use to solve a system of equations. And we've been focused on these algebraic techniques to this point. So we've talked about solving a system with graphing. We've talked about using substitution. We've talked about using elimination, right? We're gonna add some more techniques here coming up. But in order to do that, we have to build out a little bit of a new infrastructure, so a new kind of like a type of mathematics in order to use these techniques. So the next day or two, we're going to develop this new kind of mathematics and some operations that we can use when dealing with this type of mathematics. But eventually, it's going to circle back around to using this technique or applying these this infrastructure that we've kind of built out to solve systems. So we're going to get there. It's going to be a couple days before we kind of circle back to that, of like tying it back in, but that is where we're heading back to. But it might not be super obvious right from the get-go of like how this is going to connect, but you just have to have a little faith that we'll get back there. Do you guys want the lights out? Go ahead, stand up and turn them out for me. Alyssa, that's wonderful. Thank you. Bueno. Okay. So today we're going to start by defining a new mathematical object called a matrix. Just FYI for the grammarians among you, the plural for matrix is matrices. So there's not matrices. It's matrices is the plural. So a matrix is a rectangular array of elements. Now, those elements could really be lots of different things, but in this course, when we say that, it's just going to be numbers or variables. But there's other, things that we can use mathematics on that could conceivably be put inside of a matrix, but that's kind of beyond the scope of this class. So here we're just going to be worrying about matrices that have numbers or variables in them. So let's kind of look at the notation here. So typically we name a matrix with a capital letter. And to indicate the array, I'm going to use like a square bracket. To indicate my matrix, and then I'm just going to write my numbers kind of in an array. If you go Googling around, just as a heads up, some people use the parenthesis instead of a hard bracket like that. I'm always going to use the brackets when I write, but it's not incorrect to use a parenthesis. They're used maybe 60-40 bracket to parenthesis, but like, whatevs. Just wanted to point that out in case you go Googling around or look up something in another book or whatever. I don't know what you guys do. But just so you're not confused, it's just an alternate notation. Is everybody okay with that? So if I look at this matrix A that I've written up, one thing we might want to be able to do when we talk about this matrix A is to be able to describe the shape of the matrix. So the way that we'll describe that is with something called its dimension. If you're going to describe the shape of this matrix, how would you describe this? Just from a practical standpoint, if you were trying to tell your friend like to redraw this or rewrite this without them able to look at what you have on your sheet of paper, what kind of information would you tell them if you weren't telling them exactly the numbers to write? Well, you might talk about the number of rows and columns that has to be in the array, right? You're going to have 2 rows. The rows go left and right. And you're going to have 3 columns of numbers. Everybody agree with that? So that's how we're going to describe the dimension, or that's what we're going to call the dimension of our matrix. So we say the dimension of a matrix, and the way we denote that is we write dim of A, so the dimension of A, is the number of rows by the number of columns. So if we're talking about the matrix A that we wrote up here a second ago, we might refer to that, or we would refer to the dimension of that as 2 by 3. We have 2 rows and 3 columns. Again, rows are going left and right. Columns go up and down. We always, always, always write rows first and columns second when we write a dimension. You'll never write it in the reverse order. It would be incorrect if you write it in the reverse order. So always rows first and columns second. Is everybody okay with the idea of a dimension? Pretty simple idea, right? What does this remind you of when we write something like 2 by 3 like that? Yeah, like the size of a room or something, or a piece of wood or something, right? Just describing the dimension of something, just like we would in a physical world, right? Like this room is maybe 10 by 15 or something. If you've done anything around the house, that's a common thing you might say. If you're trying to like buy carpet for a room or try to paint a wall or something, these are all things that you might be interested in, or might need to describe what it is you're about to do. Okay, so another thing that we're going to want to be able to do is we're going to want to be able to refer to the specific elements inside of our matrix. So for example, let's say we wanted to talk about this number, -3. Actually, let me say this number, +10. So we can certainly imagine that there's a matrix that has more than one +10 in it, right? Everybody agree with that? So we need to have a way to describe specifically the element that we're wanting to refer to. So the way we're going to do that is we're going to describe its location inside of the specific matrix. So in this matrix A, the number 10 is in the second row, and the first column. And that'll refer specifically to this number 10. Is everybody okay with that idea? So the way we'll do this, or the notation that we'll use to do that, is going to be the following. Okay, we refer to a specific element from matrix A. We're going to use the lowercase letter a so that we can tell that it's coming from the uppercase A matrix. And then as a subscript, we're going to use the row number, comma, the column number. So we're going to refer to the row that it appears in and the comma, the column that it appears in. And that'll refer to a specific element from that matrix A. Okay. So if we go back to our previous example, we're talking about the number 10. We noted that 10 was an element inside matrix A. It occurs in the second row and the first column. So we would say that 10 is equal to A2, 1. What about -3? What is -3? Well, it's in the second row and the third column, so that would be A2, 3. We all okay with this naming convention? Hopefully this feels pretty natural. Should remind us a little bit of describing the location of a point, right? We have that horizontal direction and then the vertical direction as like an ordered pair. We're kind of doing the same thing here. Is that okay? Okay. So we've talked about what a matrix is. It's just this rectangular array of stuff, numbers mostly, or numbers and variables. We've talked about how to describe the shape of that array by describing the number of rows and the number of columns. We've talked about how to refer to a specific number from that array by describing its location. It's in this specific row in this specific column. What we want to do now is start building out some mathematical sense about how these matrices interact with each other. The first thing that we need to do is we need to define what it means for two matrices to be equal. Right? That's the most fundamental relationship in mathematics, is how do you know when two things are the same? So we're going to say that two matrices are the same if and only if. So the IFF is just an abbreviation for the phrase if and only if. Do you guys remember that from geometry? You might have used that last year in your geometry course. Some people remember doing that. Some people in the other honors class didn't remember that, but that's okay. It's just a little abbreviation. Okay, so what would we need to say for two matrices to be equal? What do you guys think? Let's just use some natural intuition. We haven't given you anything that you would need for this, but Sergio. Oh, okay, so they have to have the same numbers inside of them. So would we say then that these two are equal?
Oh, like the same numbers and like the same spots.
Okay.
Yeah.
So the same numbers in the same spots. Okay. So would you say that these are equal then? No. Okay.
Well, wait. Well, no.
They're not totally the same. What other piece is missing from having to have the same numbers in the same spots? So the same dimension, right? So those are the two things, right? So we need the dimensions to be the same. So the matrices have to have the same shape. And the elements in the corresponding positions have to be the same. So ARC has to equal BRC. Ava?
Example about how is like 10 equal to A21, because if the rows go right to left, wouldn't it be the opposite?
So when we say the rows go right to left, we're saying this is one row, this is the second row,
Okay.
and the columns, so that's row 2 that the 10 is in, correct?
Yeah.
And the columns go up and down, so that's column 1, column 2, column 3.
Okay. Thank you.
Yep. Does that feel okay?
Yeah, I was like looking at it. Like,
Yep. No, that's okay. Again, like when we say the rows go left and right, it's easy to think, okay, so each number is from left to right is a new row.
Yeah.
Yeah, rows are just like reading like a line on the paper
Okay.
is like what we mean by a row.
The blue is a row.
Yes,
Okay.
blue is a row. And that's good. Very important that we're able to tell the difference between rows and columns. So if we need to straighten out that vocabulary, that's really important that we do right away and make sure that we don't have that backwards, as that'll create whole messes of problems kind of going forward. Okay, so we've seen two examples of two things that are not equal, right? The first one is not equal because the locations of the numbers are not the same, right? It's easy to see that A11 is not equal to B11. The second one is not equal because we can see that the dimensions of A and B are different. For them to be equal, they need to be exactly the same in every way. So you have to have the same shape and the same stuff inside the shape. Is everybody okay with that idea? Even to the point that, like, those are not equal. Right? Has the exact same stuff in them in pretty much the same locations, right? But the dimension is different. Everybody get it? With what we mean by equal? So, if we know that two matrices are equal, we can do some algebra with that. So let's say we're given this and asked to solve for x. What we're given are two matrices that are equal, correct? What can we say about the what can we say about the elements then, if the two matrices are equal? The corresponding elements have to also be equal. So I can say that, for example, 4x plus 5 has to equal 11. And now it's trivial, right? Is everybody okay with that idea? I just wanted to illustrate how we're using the definition in both directions. Since it's an if and only if statement, I can look at two matrices and try to determine if they're equal by checking to see they have the same shape and the corresponding elements are all equal. Or if I know the two matrices are equal, I can set the corresponding elements equal to each other. Right? You can use that definition to go both directions. Is everybody okay with that idea? Okay. Okay. So we've established this new object that we can do stuff with called a matrix. We've established when two matrices are equal to one another. Let's start introducing operations that we can do on these matrices. So let's go all the way back to elementary school. You've been introduced to numbers. What's the first operation you learn to do with the numbers? Add, right? Yeah, addition. Perfect. Guess what we're going to start with for matrices? Adding. Okay? Okay. So, two matrices, A and B. A plus B is defined if and only if the dimension of A is equal to the dimension of B. We can calculate A plus B by just adding the corresponding parts together. So let's do an example here. So let's say we have this matrix A and this matrix B. What do I get when I add them together? You can't. Very good. Why not? The dimensions are not equal. So what do we write here? We just write that this is undefined. What if we have C as the matrix? Here. Can we add this A and C together? Yes, right? Yes, Jack?
So is there any way A and B could be added together, or is it just not possible?
Not possible if the dimensions are not the same. This pair, though, A plus C, can be added together, right? What's the dimension on A? It's a 2 by 3. The dimension on C is also 2 by 3, as opposed to B, which was a 2 by 2, right? So A plus C we can add together. Okay. So the way we're going to get the first element in matrix A plus C is we're going to take the first element in A and add it to the first element in C. So we're going to take A11 plus C11 and add them together. To get our next element, the element in the first row in the second column, that's what I'm writing underneath it, is just the position in the matrix. That you don't really need to do that. I'm just putting that in there for the note so you can see what it is that I'm doing. We're going to add A12 plus C12 to get the element in the first row and third column. We're going to add A13 plus C13 and continue doing this, right? Now, most of us probably wouldn't need to write this out because all we're doing is adding some numbers together. Like, this is not difficult. And I agree, it's pretty easy. And I would not expect you to do all that work. I would be perfectly fine if we just wrote the answer, because it's pretty easy to calculate that without actually writing anything down. And that's perfectly fine. But these are notes, so I wanted to at least introduce a little bit of notation that we'll probably want later on when we do some things that are a little bit more complicated, so we can explain how we got things. Is that okay with you guys? Questions about? Yes, Amy.
So you can only add them together if they have the same dimension, but you don't need the same numbers inside.
Correct. They don't have to be equal in order to add them together. Just their dimensions have to be equal. And that's an important distinction. I'm glad you asked to clarify. Is everybody okay with that? And that should make sense why we need the same dimension. If we're adding the corresponding parts, like if I was trying to add A and B, what would I add the 5 to? There's nothing in B to add it to. So it doesn't really work. You get what I mean? So you got to have the same dimension, because how are you going to finish adding? Okay. So let's talk about now that we've talked about matrix addition, right? We should understand how to add two matrices together. It's pretty easy. Let's talk about some properties So what we're going to do is we're going to think back about some properties we had for real numbers with addition, and we're going to see if these properties hold or there's a corresponding property that holds for matrix addition. So probably one of the fundamental things that we know about real number addition is that it's commutative. By that I mean that 2 plus 3 is the same as 3 plus 2. For all real numbers, that's true, right? Everybody's okay with that notion? Do you think matrix addition is commutative? In general. Can I take any matrix and have A plus B is equal to B plus A? Be careful here. The answer to that is no. Why? Where could there be a problem? What was that? Somebody mumbled something. Negative numbers isn't going to be a problem for us, just like it's not a problem with real number addition. Let me rephrase. Can I always add two matrices together? No. So that's the issue. So how would we change our statement for commutativity for matrices so that it is true? Very good, yes. So we can say, did I change my color or not? I don't remember if I did. Good. So we'll call this commutative property of matrix addition. A plus B is equal to B plus A if and only if the dimension of A is equal to the dimension. Everybody okay with that idea? So again, doesn't work for every matrix A and B, but every matrix A and B that you could add together, it does. So, you know, like it needed a little minor modification, but not much, right? Everybody's okay with that? Okay. So another special property that the real numbers have is that there's a unique number called the additive identity, or if you add anything to that additive identity, you just get that same number that you added to it back, right? That special number for real numbers is the number 0. There's only one additive identity. It works for every real number. 0 plus anything gives you that same number back. Everybody agree with that? Is there an equivalent property for matrix addition? Kind of, okay. So what do we lose in going from matrix addition or from real number addition to
Oh,
matrix
no.
addition?
Because you wouldn't be, yeah, no. Yeah.
So if every number in the matrix is 0, it's going to act like an identity element. What part did we lose, though, from the real numbers to matrices? What we lost is uniqueness. So each dimension of matrix has its own additive identity, right? The additive identity that works for a 2x2 matrix doesn't work for a 2x3 matrix, right? We need a new 2x3 matrix that's all full of zeros. That's what we lose. But we do have, now that additive identity is unique for that dimension, right? There's only one 2x2 matrix that acts like the number 0. But there's lots of these because you need one for every dimension. Is everybody okay with that idea? Okay. Oh. I guess I don't need to say for matrix addition if I say additive identity, huh? Let's say for any matrix A with dimension, I'll write it that way. Okay. So for any matrix A with dimension R by C, there exists a unique matrix O where the dimension of O is also R by C, and each entry is equal to 0. Why do you suppose I chose the letter O to represent the additive identity for matrices? It's kind of obvious. It looks like 0, right? What's it acting like? 0. So why I'm going to pick O? Because it looks like the number 0. It reminds me of that. So if A is a 2x3, O would look like this. Is everybody okay with that idea? Okay. The next real number property of addition that I want to talk about is the inverse property. How did I start this? Okay. Okay. So real numbers have additive inverses. So for any real number A, there exists some unique real number B. We call that number B the additive inverse, such that A plus B is equal to 0. Now, we have a special way that we represent this B for real numbers. What is B really? What was that? Somebody said something. It was quiet and soft and masked. I think it was right though. Negative A. Yes. That's it. So for example, the additive inverse of 5 is negative 5. The additive inverse of negative 7 is positive 7. This is not surprising to us, right? This is something that we've, known for a long, long time. The question now is, do we have the same thing for matrices? If I have some matrix A, can we find another matrix that when I add it to A gives me the matrix of all zeros? Yeah, so what does the shape of that matrix have to look like? The same as A's. But what do all the entries have to be? The opposite signs of the entries in A. Everybody agree with that? Okay, so let's write that down. Maybe we should write it the other way. That probably makes more intuitive sense. Come on, you stupid machine. Since we're talking about B. Okay, for any matrix A, there exists a unique matrix B such that A and B have the same dimension, and the entries in B are just the opposite of the entry in A. That means that A plus B gives us 0. So we'll call B the additive inverse of A. And I heard at some suggestion here of a symbol that we can use to refer to B. Somebody suggested we call B negative A. That's the symbol that we'll give it. Just like we did for real numbers. Yes, of course. Okay, is everybody okay with these three ideas? Let's just kind of put them together here with a couple of examples and just do a little actual arithmetic just to make sure we got it. Sound good? So let's say that A is the matrix 2, 5, negative 1, 6. What's A inverse going to look like then? Good. Everybody's okay with that? And then if I add A and A inverse, what should I get then? Yeah. This matrix that's full of zeros. Is everybody okay with that? Real quick, what does this operation look like? Subtraction. Guess what we can do now? We're going to define matrix subtraction. Oops. I think that's now operation number 2. So since we've established the existence of these additive inverses, we can just define subtraction the same way we did for real numbers and just say, oh, A minus B is the same thing as A plus negative B, provided that the matrices have the same dimension. Is everybody okay with that idea? Probably no example necessary for that. So let's do another example, and this will kind of spur us on next operation here. What's a plus a give us? Well, it'll be and you want to call that 2a, right? That's what everybody wants to be able to do. Does that feel okay? Good, right? We want to be able to do this. Everybody agree? We want to be able to say a plus a gives us 2a. So that's going to become a new operation. We're going to call this scalar multiplication. Actually, let's say I'll just write in words. That's probably the easiest way to do it, and then try to use any symbols here. So for any matrix A and any real number k, we refer to k as a scalar. This k is a lowercase k. We're always going to write it as lowercase k. Now, I can't tell the difference between my lowercase k and my uppercase k, but I'm just letting you know that that's supposed to be lowercase. We call k a scalar. So that real number that we use to multiply our matrix by, we call a scalar. It's just a vocab thing. And the way we calculate k times a is just by multiplying each entry in a by that number k. So if we have the matrix A and we want to find out what 3a is, well, I just take that 3 and multiply it by each of the entries. Is everybody okay with that idea? Again, pretty easy to do this calculation, right? No big deal. So we have addition, we have subtraction, we have one kind of multiplication. What property comes to mind when we have addition and multiplication now? Distributive property. Is there a distributive property for scalar multiplication? What do you think? There best better be if we can do a plus a gives us 2a, right? There best better be. So we do have a distributive property. for matrix addition, scalar multiplication. And there's really no caveat here other than you need to be able to add the two matrices together. The distributor property works exactly the way that it did before. So let's say that we have Sergio. Look at the example we're going to do. You betcha. Could be a fraction, could be a weird number like the square root of 7 or something. K can be any real number. Could be 0. It's kind of trivial if K is 0. What are we going to get if K is 0?
0.
Nope. The identity matrix, which acts like the number 0, but that is not 0.
Wait, what? Yeah, I guess.
Right? It's a matrix full of zeros, not the same thing, right? So you got to be careful. Okay, so let's do this example here right quick. Oh, I didn't write down what we're doing, huh? Let's say we want to do K times A plus B. So one option is that we could do the addition first, and then do the scalar multiplication second. Or we could do the distributive property and we can do the scalar multiplication first. And the addition second. It doesn't matter. That's the point, right? That's the beauty of the distributor property. You can kind of do whichever one seems the easiest. To me, adding first and just doing one scalar multiplication seems much easier than doing two scalar multiplications and adding. But, you know, whatever floats your boat, man. That's cool. Is that okay? Okay. Last thing we're going to talk about today. So far, everything has been pretty straightforward, right? These operations have been pretty easy. They've kind of worked the way you'd hope they would work, right? Equal means things are exactly the same. Adding, we just add the corresponding parts. You know, like subtraction, we subtract the corresponding parts. Scalar multiply, we just multiply everything by it. So far, this has been pretty good, right? Everything worked in kind of very intuitively. Today, or right now, is things are going to start changing here a little bit. So we have our fourth matrix operation. This is called matrix multiplication. And here things are going to change and get a little weird. My recording stopped for a second. The recording or the product of two matrices A and B is defined when the number of columns in A is equal to the number of rows in B. That's already rather strange, right? In fact, if the dimensions are equal, they might not be able to be multiplied together. Let's look at a little example here. So if A is a 2 by 3, and B is a 3 by 5, can we multiply these together? Yes. So the number of the number of columns in A and the number of rows in B is equal. This is defined. We can do this. Versus something like, if we just reverse it, this you cannot multiply together. We have yet to say how we're going to do that multiplication, but already determining whether you can do the multiplication or not is a little bit complicated, right? So you want to know the story of how you can remember how to do or how to tell if two matrices can be multiplied? Here's the story. Multiplying matrices is like falling in love. When two people meet, if they're kind of the same on the inside, they can fall in love even if they look different on the outside. And when two people fall in love, sometimes they'll have a child, and that child will look a little bit like the first person and a little bit like the second person. So the matrix that results from A times B will be, in this case, a 2 by 5. It'll be the number of rows from the first matrix by the number of columns in the second matrix. Isn't that romantic? I love it. When you steal this idea to write like $1 million romantic comedy screenplay, I don't need any money back. You can just like name a character after me or something, no? For you creative ones in the classroom. All right. Does that feel okay so far? We have yet to talk about how we actually do the multiplication. We're going to do that in a second. Let me turn this into something that resembles grammar. Okay. So what we're going to do is we're going to multiply each item in each row of A by each item in each column of B, and then add those together. Let's do a concrete example because this is kind of a visual procedure, and it helps very much so to look at a concrete example, and my symbolic instructions are probably not super duper helpful. An example is going to be much more useful. Is everybody okay with that plan? Okay. Okay. So here's a matrix A and a matrix B. Before I start doing anything, I want to check to make sure that I can actually multiply these together. So I notice that the columns in matrix A and the rows in matrix B are equal. Everybody agree with that? So what I'm going to do, in addition, I also know the shape of my resulting matrix. My resulting matrix will be a 2 by 2. So at least to start, my suggestion is we draw our matrix, our 2 by 2 matrix, and we put a blank here for each one of the elements, and I included the location of that element. So the first blank is in row 1, column 1. The second blank is in row 1, column 2, etc., etc. Is everybody okay with that? Just like we did before. So this is what my answer is going to look like. So to calculate this first blank, I'm going to use the elements in row 1 from A with the elements column 1 from B. So I'm going to have 1 times 7 plus 3 times 4 plus negative 2 times 2. Everybody okay with that? And I'll do that addition and multiplication here in a minute. The next spot, I'm going to use row 1 from A and I'm going to use column 2 from B. I have 1 times 9, 3 times 10, and then negative 2 times. So far, so good. Now I'm going to move to row 2 for A. And I'm not going to highlight those things just because the purple makes it hard to read, it seems. And I'm going to use row 1 from B. 5 times 7 plus 0 times 4 plus 6 times 2. And I'm just going to kind of underline with the purple there. And then I'm going to use row 2 from A and column 2 from B. So let's see, I have 7 plus 12 is 11, or I'm sorry, is 19, minus 4 is 15. I have 9 plus 30 plus 10 is 49. I have 35 plus 0 plus 12 is 47. Then I have 45 plus 0 minus 30 is 15. So my answer is 15, 49, 47, 15. We'll do some more examples of this when we meet back again next week. But I want to leave you with one thought here for the weekend in addition to a short homework assignment. Right away, when we looked here, we saw that A times B has an answer, but B times A does not have an answer, right? So not all matrices, when we multiply them, are going to be commutative. Right? What I want you to think about over the weekend is see if you can come up with any situations where A times B does equal B times A. Think about that. We'll talk about that in a good detail on Monday. So if you don't come up with anything, that's fine. Or if you just have like some harebrained ideas, that's good too. Like I want to talk about it and explore a little bit with that. So I want you to think about it. You'll notice in the content library, I've posted 3 new homework assignments. The only one due this week for you guys is homework 8. So this will be your homework check on Sunday, will be this homework 8. It's just doing matrix addition, subtraction, and scalar multiplication. There's no matrix multiplication on this assignment. I want to talk about that more next week before I ask you to do any of that. Okay? So it's just these 10 problems. Should be pretty easy. Everybody feel okay after today? Okay, good. We're done.